passing to the third lecture on the QKD architecture, the application layer, that will be made by Dr. Omer Papadopoulos. He's a functional researcher at the SCSRD Demokritos and co-founder of the startup Synthesis. Omer is our LSQCI expert on standards and certification, and he has more than 20 years of research experience. Omer, the floor is yours.
I will try to be short. Yeah, sure. How? This way? Yep. Okay, there is no meaning. First of all, I see a lot of young people here, meaning that some of you may not be aware of what exactly we are talking here. We are talking about the QKD, and the question is what QKD is providing. The QKD is providing keys, and if you ask me what is a key, the key is just a random number, bits, random. So what we do with these random numbers, we take a text information, we mix them with some black box or whatever, and we create the cipher text, which is something that the adversary can understand. This is what we are discussing all day here from the morning. And the market of QKD is the key cryptography. It's not code cryptography, other modes of cryptography, it's key cryptography, meaning that we do the cryptography with random numbers, which is the key. And who is providing the key? The QKD. We have two boxes. You have also listened about quantum safe, RSA, whatever. You have to have in your mind that there are two buckets here. Okay, in one bucket we put the cryptographic tools that are safe from quantum computers, and the other bucket we are putting those that are not safe. So I go through fast here. In the non-safe bucket, the non-quantum safe bucket, we have only the public key cryptography. The problem is that within the public key cryptography is we have built all the internet, the web, the cloud infrastructure, and this is the problem. If the public key cryptography is in danger, so all the web infrastructure is in danger. If you don't understand these terms, signature, digital signature encryption, key generation, PQC, RSA, symmetric encryption, I invite you to join tomorrow the session we are having for 1 hour and a half, where if you don't know anything, you will start learning from scratch, from zero, and all these terms, and we will help you go through to be able at the end of the session to be able to get the keys from QKD. You will do it by yourself. Take the keys, encrypt a text or something, a photo, sign it digitally with a PQC, and then send it to another one chatting, let's say through chat or whatever. So just join tomorrow for those that are not familiar with these terms, and we promise that you will get a lot of value out of this. I don't want to go through what is the problem with QKD. The previous speakers mentioned and described very well the problems. We have a device, generates a key, but there are problems. One of the problems of education, and etc., etc. So we have a box. We bought the box. The box has some problems. What we are doing with this box? There are some thoughts that we can, let's say, try to complement this box, the QKD, with other technologies that are more safe. For example, the PQC. We will explain tomorrow what is PQC. We will explain what is lattice-based, etc. And there are efforts worldwide somehow to complement that. Why to complement that? Because QKD, as the previous speakers described, is information theoretical construct, meaning that if you have a computer that has unlimited power, you can't somehow broke the code. And we have the PQC, which is easier to implement, but it's computational security mode. What does it mean? It means that if you have unlimited power of computing, then there is a risk for PQC this to be broken. So what if we combine these two somehow to complement these two somehow? What will be the outcome? The problem is the following. The EuroQCI, the domain, I mean, the community are working, released a CONOPS, concept of operations, last year, saying two things. The first is that I want the QKD service, I mean, how the QKD systems works and transmit the keys. This service, I don't want in this service to see PQC. I don't want to see any public infrastructure, public key infrastructure. I want to see only physics or symmetric encryption. This is the case. But in the first one, says that, okay, when you get the key, you can, let's say, mix it with PQC. What it says, let's see visually what does it mean. It means that, as George and Yannis described, we have this system. We have the QKD systems that generates the keys. We have the KMS that distributes the keys around. And the CONOPS says that this is my domain. This is my domain, and I don't want to see in this domain any public key infrastructure. I don't want to see anything, PQC systems or RSA or whatever. That's fine, but we are having the other domain, the vertical ones, which means that we get the keys from the KMS systems and we push the keys to the applications, to the encryptors, or whatever. This is open. They suggest somehow some techniques to mix QKD keys with PQC, etc., etc. But this domain, the vertical domain, belongs to the end users, to the vendors, and they will decide how to use their PQC. Okay? So we don't want to see PQC in the horizontal based on the CONOPS, but we are free to utilize PQC in the vertical aspect. Let's see some use cases of how we can combine. The first thing, we can combine QKD and PQC. We take the keys, we mix the keys, we generate more keys, and if we do that, then we can support, let's say, symmetry, some symmetrical encryption that need big keys. Okay, the QKD, the main aspect of QKD is very slow. It generates small piece of keys. So if you need an algorithm, if you need a service that needs a big keys, then QKD is not the appropriate issue, device. In that case, you have to mix it and somehow generate pseudo, let's say, random keys. The other issue we have to see here is that, okay, our friends in EuroQCI don't want to see in the yellow PQC, but why not somehow to try to create a resilient channel, a parallel channel? So if there is a failure in the QKD system, then the parallel channel to be there and try to cope with this failure. So to answer if PQC and QKD are complementary or competitive technologies, I would say that they are competitive because they are doing the same job. But they are doing the same job with different characteristics. So the final issue is we can somehow try to complement the two, to integrate the two technologies in some aspects in order to provide a better and more secure service. Regarding the PQC, if you don't understand PQC, what is PQC, please join tomorrow the event. Harris also will describe what is PQC, and in our presentation we will focus on that. Just to tell you that a few weeks ago, the three standards, the three PQC standards released by NIST, it's the Crystal Kyber, the Lithium Sphinx, and we expect the other protocol to be released late 2024. Already, there is effort, for example, in ITF organization, to somehow create a new TLS version where they try to integrate and use classical RSA with PQC. Why they want to do that? Because they want to keep working with the classical, because it's very difficult now to change every system in PQC. And if the quantum computer comes, then they will change to PQC. So this is the case. If they manage to create this TLS 1.3, let's say, library, in that case it will easier for vendors to adopt PQC, for example, to use PQC in their websites, etc. These are the two main algorithms we were facing, and we are working with these algorithms almost 2 years now. It's a Kyber and dilithium. We use one to encrypt the data, as we said, to mix with a key and encrypt the data and send it securely. And the other is dilithium, which is to digital sign. I will go through these two algorithms tomorrow and will explain exactly how they are working. They are based on learning with errors over lattices algorithm, which is the case. The classical cryptography we are using now, RSA mainly, and Diffie-Hellman partly, they are using algebra problems to make the problem difficult. These algorithms are using geometry to create the problems that is quite hard for computers to crack them. These are the challenges of deploying PQC. There is no need to go in detail now. We will discuss these challenges tomorrow, why there is a problem with PQC. I wanted just to give an overview of what exactly we are doing in LSQCI. Dr. Huber mentioned the theorem of Mosca. What does it say? It says that in order to start working in an area and start changing your algorithms to go for quantum safe algorithms, QKD, PQC, etc., you have to find if this domain needs to start working on these technologies now. How do you find that? By looking if this domain has data that has to be kept secret for a long time, etc., etc. If we see in this McKinsey framework, we see that life sciences, healthcare, medical, is one of these domains that needs to start thinking to adapt these quantum safe technologies. There are many aspects and there are many areas in healthcare where you can implement QKD, from healthcare repositories, from transition of data, from e-health services, etc., etc. What we want to show here is that if you want to do the change from the classical to the PQC or the QKD system, it's quite complicated, very complicated to do the change, to go. Consider going to a hospital and say, I will change the RSA to the PQC. This is very, very difficult because there is very complex infrastructure. And in that case, in our pilot, what we did is that we don't touch anything. We go to the organization we are working with. We say, keep working with your systems. We will not touch anything, but we will create some applications. And if you like, you can use these applications, that these applications are using QKD and PQC. Okay, so if you don't feel confident or if you want to secure more some of your data, just use our application. I mean, just press and open our application, nothing more than that. And it seems that it's working. In our pilot, we are connecting the Alexandra Hospital with our premises in Demokritos. In our testing, we are using all the synchronous, secure, quantum safe secure synchronous encryption techniques. OTP Chacha 2020 and AES 256. We will describe these techniques tomorrow. These are some of the implementations. This is the first naive implementation we did. We expect you, if you attend tomorrow's telco event, training event, to be able to identify why this is a naive and why this is risky. This is the case. I mean, at the end, we will ask you, can you identify what are the risks of this implementation we did initially? What we did, in fact, is that we get a QKD, we got an encryptor, and then we try to send the messages from the end users to the encryptor and send these messages to the other endpoint. We didn't like that. We will explain tomorrow why we didn't like that. And then we change the whole architecture and we bring the keys to the end user and we allow the end user to use the keys and communicate with the other user. Why is that? Tomorrow we will tell you the solution. Also, we don't do that. Also, we created a signaling server, a WebSockets signaling server. What does it do? It allows the users to communicate online, exchange data. Otherwise, they have to use, let's say, encrypted data and then use the email and send it. No, with our signaling server, they just use the server and communicate online with the other user. Now we are having only chatting and the file exchange, but video is on, it's coming. Also, one of the things that we wish to implement, we are implementing in fact, but we wish to validate and test it and see if this will work and in real life scenario is to allow, let's say, the doctors, but within the doctors you can put anyone else, to send automatically through this network to take the keys from the QKD and encrypt the data and automatically through our system to send it to a repository, let's say an electronic health record, for example. The electronic health record again communicate automatically with the QKD, gets the keys and be able to encrypt it or decrypt it or whatever. We will see the scenario. This is very important. We have here that the communication is with Chacha and the AS256, but we will also consider, we don't have it here, to put another layer, as AIT showed, to put another layer inside the VPN. We will try to see if this will work and we will do some experiments on that. This is what we will do tomorrow. You will be able, you will understand, you will have these two software at the end, and you will be able to create certificates, to sign, to communicate with QKD, with this one, to get the key, to write a text or upload something, to encrypt it within these 3 encryption protocols, and then use the other one to sign this text or this encrypted text and send it to sign digitally with dilithium PQC algorithm and send it to the other one who will be able to decrypt it, meaning that you will be able to communicate using QKD and PQC. And this you will do it yourself. No need to stay on that. Again, no need to say about the training. We have all our content there. Thanks very much, and I'm waiting for you tomorrow. Thanks very much.